Now let's we look at the natural coordinate system, where in these sessions we are going to start to look at our elements in a new coordinate, which is known as the natural coordinate system. The coordinate system has a non-dimensional units. So consider a single element as we have in figure A here, where, for example, if we take n elements where the nodes A is node number 1, nodes number 2, and the point at, which is the point of interest that is located between the two nodal points within our element, and this distance in the Cartesian coordinate system is located at a certain distance from the datum, and this is our datum that is located at the origins in the x direction. And in natural coordinate systems, so the similar element can be viewed in this natural coordinate system, where from the textbook that we refer and we use as our main reference in this course, it will take the natural coordinate system, which is labeled by z, and the value will be always -1, which is on the left hand side of our elements, and the value of z will be always +1 on the right hand side of our elements. And by taking these assumptions, z equal to -1 and z equal to +1, then we can define a natural or intrinsic coordinate system z, which is given by 2 over x2 minus x1, which is actually will give the length of this particular element multiplied by distance of x minus x1, then minus by 1. Then it's mentioned here that z coordinate will be used to define shape functions later, and required to establish an interpolation function for the displacement field within the elements. Alright, when we solve the system of a linear equation in the form of a k, q equal to f, actually will give us the informations of displacement at each nodal point. So when we solve this kq equal to f, then actually it will give us the q at nodes number 1 and the q at nodes number 2 on this particular element. So this q here actually refers to the displacement, which is we calculate or predict exactly on the positions on the nodal points. But the deformation or the displacement anywhere in between these 2 points is actually unknown, still unknown, but it can be determined, which is by taking the displacement at or within the 2 point here, which is we call it as a displacement field, a ux. Then for simplicity, it is assumed that displacement varies linearly from nodes 1 to node 2. So this we use a linear variation between the two nodes in terms of displacements, in terms of stress and strain. This is actually just the limitations of our discussions in this course, but the distributions of the displacements may not always linear. It may follow certain curve as shown in figures on the left hand side here, which is maybe follow certain cubical curve, polynomial curve, or maybe other type of curves. But in our discussion, we limit this to the linear variations or distributions of displacement at one point to another. So in this case, by taking linear variation between the 2 points, then we can establish a linear interpolation functions to represent the linear displacement field within the elements. Then to implement this, linear shape functions are defined, which is given by these two interpolation functions, n1 as a functions of natural coordinate system, which is given by 1 minus z over 2, and the second interpolation functions n2 equal to 1 plus z over 2. So in the exam and also in the test, the student do not need to remember this equation as we will supply this. But the most important thing here, you need to understand and know where you want to use this and how to use these equations in solving the finite element method. The field displacement within two nodal points can be obtained as we mentioned in earlier slide, that the variations of the displacement at the two nodal point will assume varies linearly between the 2 points. So thus the field displacement here can be predicted by using the linear interpolation functions as given by n1 q1 plus n2 q2, where we can substitute the n1 and n2 into this equation that gives the second equation in this slide. And this equation can be also can be written in metric form, which is equal u x equal to nq. But as we can see here, the term u here is still written in the Cartesian coordinate systems, which is n contains n1 and n2, and q, which is contain displacement or known displacement or calculated displacement at node 1 and node 2. The value of n1 and n2 actually can be determined for given geometries of our elements. For example, if we know the positions x for the nodes number 1, we know the position of x at point number 2, and then we know the positions of x or distance of point P. For example, we got point P of our from our system, then we actually can determine the value of n1, n2, and also the natural coordinate system at this particular point P. So let's look at the first example here. Let's say we have one element spanning from nodes number 1 and nodes number 2, and then we have the location P, which is the location of interest, which is located at 24 inch from the datum. Nodes number 1 is located at 20 inch from the datum, and nodes number 2 also is located at 36 inch from the datum. So from there, we would like to determine the value of z n1 and n2 at point P. So what is the value of z at this particular point P? Where in the first place, we already know that z will be 1 at nodes number 2, and the z at point number 1 will be equal to -1. But what is the value of z at point P? From the given coordinate system, actually we can easily determine the value of z n1 and n2 at point P. So given that the natural coordinate system is given by this equation, and substituting the x2, x1 and x in this equation will give us that the z or the natural coordinate at point P equal to -0.5. So that's mean here, so the midpoint between -1 and 1, so the midpoint somewhere there where we have z equal to 0, then the point P here, according to the value, is actually located in between the midpoint of these elements and the elements and the nodes number 1. So it is actually located at the midpoint between 0 and -1. From the calculated value of z, we can supply this information into the shape function n1 and n2. Then we can obtain the value of n1 and n2, which is equal to 0.75 and 0.2 respectively. Then given that the displacement at point P is to be determined, so we have this, and we know that q1 is given by 0.003. So this is our q1, which is q1 is obtained after we solve the system of linear equation. And then we know that q2, which is given by -0.005. so that's mean here our q2, which is actually is moving in this direction. This is our q2. So this element actually is under compression. If we look at this, the two values of q1 and q2, and supplying n1 and n2 as we obtain from these above solutions, then we will find that so this is the mid, so the point P is located there. So at point P, we can see that these elements here exactly at point P is still experiencing some deformations, which is directing or moving on the right hand side with 0.01 inch